It is my pleasure to introduce Dr. Prasanta Kundu. Uh, Kundu sir was my supervisor, PhD supervisor, and it is my pleasure to welcome Kundu sir after a long time uh, for this particular session. Sir has received his bachelor's degree in electrical engineering from BE College, Sipur, University of Kolkata, uh, which is now known as IIEST in 1992. Master's degree in electrical engineering again, with specialization in high voltage engineering from Indian Institute of Science, IISc Bangalore in 1994. Sir has pursued his PhD in electrical engineering from IIT Kharagpur in 2009. Presently, sir is working as associate professor in electrical engineering department with SV National Institute of Technology, NIT Surat, since 2000, since August 2000. Before that, sir has more than 6 years of industrial experience, again in the field of high voltage engineering. Sir was a recipient of 2007 IEEE DEIS Graduate Student Fellowship. His area of research is condition monitoring, application of DSP techniques, electromagnetic field computation. Sir is a senior member of IEEE and fellow of Institution of Engineers, India. Sir has published more than 100 research papers in various national and international journals and conferences. And sir has guided number of PhDs, 7 completed and 6 are pursuing PhD under him. I was also, as I said, one of sir's students. So I believe that whatever knowledge in signal processing, artificial intelligence, machine learning that is that I have got is from sir only. So I request sir to start his session. It will be very interesting. Please be with us with up to 9 o'clock, right? So all the participant, please attend the session. Thank you, sir. We can start.
Okay. Uh, so is it visible now?
Yes, sir.
Yeah. So welcome to this session. This is related to the partial discharge monitoring for power equipments. This will be the contents of this talk, the partial discharge measurement. We'll talk something about the fundamentals of the partial discharge measurement, then partial discharge in rotating electrical machines, and partial discharge in cable. So first, the partial discharge measurement. If you have the background of the high voltage and partial discharge, then it is okay. Otherwise, if you don't have, we'll start from the little basic knowledge. Now, partial discharge, what is the fundamentals of the partial discharges and why it is important? What are the different method of detection of partial discharge? Electrical method, acoustic method, UHF method. Partial discharge is a localized electrical discharges that only partially bridges the insulations between conductors and which may or may not occur adjacent to the conductor. It signifies that whenever there is insulation, this is a high voltage phenomena. So this is basically occurs in the insulations. Wherever there is a localized electric stress is exceeds the breakdown voltage of that material, then there will be discharges. If there is a uniform electric field, then there will be less chances of partial discharges. There will be always will have a full discharges, but both the electrode will join together. Bridge. That's why we're calling it the bridge. From one electrode to another electrode, if that is joined, then we call it as a bridging. But if this one electrode has started the discharges, but it has not reached to the other electrode. So here electrode means in the related to the machines or related to the electrical devices. One is the high voltage conductor and another one is the grounded part. And in between there will have a insulation. So if there is a breakdown of the insulation, then it will reach from the high voltage conductor to the ground. So that is happening in any electrical apparatus, any power apparatus, including transformer, rotating machines, cable, capacitor, whatever we can have, that will be on high voltage part, or will have the ground or low voltage part, and there will be in between insulations. Now, if the insulation is composite, if it is having a different insulating material like solid insulating material, gaseous insulating material, or liquid insulating material, so there will have a composite insulating material. So they have different permittivity. Then the stress distributions, voltage distribution will also be different based on their permittivity and the distances and the thicknesses. So that is one way of the unequal voltage distribution. Unintentionally, sometimes there may have some voids. If we don't want to create the voids, the insulations will have some voids because of the manufacturing defect, because of the operational. Like operational means that if there is a temperature variation of the insulating material, so higher temperature, lower temperature, heating, cooling cycles, that may have a crack. So that micro crack will have a different inclusion. So that will going to create a localized stresses. If there is a localized stresses, then it will have breakdown only on that particular gap, particular portions. That is called the partial discharges. So it can be associated with the ground electrode, it can be associated with the high voltage electrode, it may not be associated with any of the electrode. Now, what is the reason to understand the partial discharges? It is the silent killer for the insulations. It will do the insulation degradation. If you think in a overall view that partial discharge will have a heat, light, and electromagnetic wave. So that heat will erode the insulation. So it will have a micro label. So even the micrometer, if it erodes 1 micrometer in one day, another micrometer one day, so over a period of time, it will kill or it will break the total insulations. That's why you have to check the whether that insulation is PD free, that partial discharge is well abbreviated as a PD. So there are different methods to measure it: electrical, optical, optoacoustic, ultra frequency, acoustic. So they all will have certain advantage and certain disadvantages. For example, electrical will tell you about the magnitudes and the intensity of the discharges, but it is very prone to interferences, electromagnetic interferences. So that's why electrical technique cannot be adapted in online cases. If one transformer is in operations, one most machine is in operation, so there you cannot do the PD measurement there because the noise will be significantly high. So electrical measurement can be done on a laboratory. So that is a problem for the electrical methods, but it can give the advantage that it can assess the quantify the PD. Then other techniques which is very less prone to the interferences like the acoustic, which can be adapted in the on-site. So it can be done online, offline, both I can do the partial discharge measurement. Now, partial discharge occurs whenever there is insulation defects. If there is insulation is a pure, then there is a very less chances of partial discharges. If the field is uniform, then there is a less chances of partial discharges. But in practice, neither insulation will be pure or neither field will be uniform because of the complex nature of the electrical equipment, conductor and its winding and the ground part core. So that's why there will have some voids either attached to the HV conductor, some voids attached to the ground and in between. So there will have a different discharges. Based on that locations, we classify the partial discharge in different type. If it is attached to the high voltage electrode, then we call it as a corona discharges. if it is attached to the high voltage electrode or low voltage electrode, but it is not in the solid insulation, it is on the surface of the insulation, then we call it as a surface discharges. But if it is in between of that conductor, then we call it as a void discharges. So whatever be the cases of the partial discharges, whether it is in between, surface or void, we can model the partial discharges for analysis or understanding with the ABC model parameter. It is well known as the ABC model. ABC means the total partial discharge site can be modeled with a 3 capacitor: A capacitor, B capacitor, and C capacitor. C capacitor indicates that where the discharge is occurring, that is the void or the surface part, that portion. B capacitor is indicating which is series with that particular component. A capacitor is other than on that part, parallel to that one. So now with this ABC model, we will be able to understand how the partial discharge is occurring and how to measure this one. So basic electrical measurement, this is a very common basic electrical measurement circuit, very brief, it is not given in details. You need to have, and this is for a lab measurement. So you need to have one high voltage sources. A indicates the sample for which you're going to measure the partial discharge, like transformer, rotating machines, cable, capacitor. K is called the coupling capacitor. It is outside on capacitor, another than the A capacitor. A is modeled as a sample. This A includes the ABC. All these 3 parameters will be part of this A. K is a separate one, is the coupling capacitor. Z indicates the quadruple or the matching impedance or the measuring impedances. Z indicates the measuring impedances. This is a dotted box, which is also a position of the Z. Z either can be placed in series with the sample or the test object, or it can be placed in series with the coupling capacitor. So any position we cannot have both at a time, but there is a measurement how you can put the both at a time. But normally either of this position in series with the sample or series with the coupling capacitor, we can connect it. So whenever there is a discharges, it will create a internal or local disturbances. So these disturbances will flow, allow some current through these impedances that will be very smaller in magnitude, in the order of millivolt, microvolt. And that is being amplified with the amplifier in a measuring devices and shown in the DSO or the oscilloscope or the PD measurement devices. This is the basic structure of the measurement one. Now with the ABC parameter, how the PD occurring, here we can understand with the AC situations. If you are applying the full voltage, AC voltages, now if you go to the previous one, say you are applying the full voltages here, this voltage will be divided based on the capacitor's value. Some voltage will come across the C and some voltage will come across the B. Total voltage will come across the B, A part. B part will be the part of it, A part will be the full voltages. So voltage at B plus voltage at C will be the full voltages. So that's what is shown here. This is the divisions of the voltages. C is the voltage across the void and PD will occur, or the localized test is higher. Now this U plus and V plus and U minus V minus, this indicates the voltage at which partial discharge will occur. If the voltage is very low, if the VC peak is lower than the U plus, then no partial discharge will occur. So for the partial discharge occurrence, you need certain minimum amount of voltage, so that the gap voltage will exceeds more than the breakdown voltage of that gap. Now, if this is exceeding, then there will have a breakdown. So this is written, but it is a statistical phenomenon. It won't occur so regularly. that whenever there is a, say, any breakdown is a statistic, it will not occur at the same voltage always. Sometime if it is occurring at 10 kV, that another time it may occur at 11 kV, 9 kV. So there will have a statistical distributions. There will have a sigma for it. There will have some deviations of these voltages. But for understanding, it is given that always that if there is voltage is exceeding more than the U plus V in positive cycle and U minus V in the negative cycle, then there will have a breakdown. So this breakdown will occur. That time voltage on this C capacitor or void capacitor will drop down to 0 or very low value, V plus value. This is the variation of the voltages. Now, since these two voltages will drop to lower value, so this will going to have a lesser voltages compared to the supply voltage. So they will going to circulate some amount of current. So this current will come from, instead of coming from the source, it will come from the coupling capacitor, because this is a very higher frequency. So source normally is a transformer which will have inductor which will offer a very high impedance. So transformer will be a source as well as a filter for the high frequency. It will not allow any high frequency current to pass or go to the sample. So that's why you will have the coupling capacitor to give that amount of current or that amount of charges to charge that C part. So as soon as this voltage will fall to 0, it will again, the discharge will disappear and it will reflect as the current pulses. And it will continue like this, and the same thing will happen in the negative half cycle. So this is the discharge pulses which is integrated and measured in terms of current. Now, so this is the basic of it. Now, if you go a little bit advanced of the partial discharge measurement, we have the very commonly known for the partial discharge measurement and for the pattern classifications where AI/ML technique is very well known adapted to classify the partial discharge is the phase resolved PD, which is all known as a PRPD. PRPD. So this is called the 5QN pattern. So I've shown two diagram. There is many you can plot this one for the different type of partial discharges. Means partial discharges occurring adjacent to the conductor, in the void, in the surface, in the very critical zone, or wherever this is occurring, they will have different pattern of the partial discharges. It won't happens in the similar manner. So this 5QN, this one. So if you measure the partial discharge for some times, for example, 1 minute. So there will be many cycles, not only for the one cycle. So you don't measure the partial discharge only for one cycle to get the PRPD. We measure for a few cycles. It may be for 1 minute, 10 minutes, or depending on the situation. So there are many cycles on that cases. Now, PD phi will not occur at the same. Phi means the phase angle. If you check this diagram, that phase angle, it will have a 0 to 360 degree, 0 to 2 pi. At any instant, PD will occur. It will not occur at the same intensity and same magnitude at the same phase at every time in every cycle. So that is the statistical nature. And because of the statistical nature of the partial discharges, because of the statistical nature of the discharges, we are having this pattern. Phase is all PD. Now, if it is occurring at one particular phi, one magnitude, that is Q, that N, then at a different cycle, it may have that same phi will have a different magnitude. Q1, then Q2, like that. So that's how you're going to have a phi angle, and this magnitude will have a different. And this number of pulses, they can have a different way of presentations. Number of pulses of that particular magnitude, we plot in the color code or dense code, like that. So this is a typical pattern of the PRPD, phase resolved PD. This is done only for the AC measurement, where we have the phase angle. Now, this is also, and you can have that PRPD in a 3D model also. 3D presentations, color code presentations, 2D presentations, the dense presentations. There are many we have the. So different type of partial discharge is going to give you the different type of pattern. And from there, if you find out the feature, and this can be fed to the any identification technique, any AI technique, and we can identify this one. So now here it is same thing, phi, Q, and N, that is count. Phase angle, amplitude, Q, and N. This is PD is measured in terms of Q, normally in terms of charge, which is integrated of that current pulses integrated over time. There is a cases it can be measured in millivolt also in terms of voltage, millivolt, microvolt, where the PD is in terms of PC is extremely high. So this different pattern we get it for the phase resolved PD. So this is few pattern is shown for the different cases. Now PD studies is done for the AC-DC combined voltages also. Inception voltage varies with the combined AC-DC voltages, and you will have the transformer cases, and there is oil paper insulation is combined AC-DC voltage specifically for the converter transformer. How the PD is going to occur? This is a typical setup for the PD measurement, similar to the previous one. You will have the sample, then oscilloscope, then this is the voltage measurement devices, and how are you going to measure? This is the DC side, and this is the AC side. DC side you will going to have in both the cases. So you will have blocking capacitor so that DC should not go to the other side of AC. This capacitor will be the blocker for the DC, but it will pass the current for the AC. It will have that omega C, but there will be block for this DC cases. Omega is 0, so it will going to offer infinity. So that AC-DC combinations of this case you're going to have. Now there is a typical applications of the AC-DC voltages. There are different PD is measured. First we can have the ramp cases, then we put the constant voltages, and then you can apply the AC cycles. PD is also measured including the impulses also. Means you can have AC and impulses, you can have a DC and impulses depending on the different cases, because in normal situations, if PD is not occurring in AC, but if there is a minor transients, that is a part of impulses. If the minor transients occur, that time PD extinguishes, or it's occurred, that you may not extinguish afterwards. So that's why you have a study of the piece. Impulses include PD in impulses in AC together to understand the characteristics. Now here some PDIV, that is partial discharge inception voltage and partial discharge extension voltage. This is also two important feature of the understanding the partial discharge other than the phi QN. It is the minimum voltage at which partial discharge will just start inception, that will just start at that voltage. So in a sample, if we keep on increasing the voltage from very low, where the PD will not occur, and at one point PD will start. Say for example, if it is starting from 0 and it at voltage of say 8 kV, PD will start. And after 8 kV, PD will continue. It will have just one pulses or few pulses immediately beyond the threshold of the measurement. And if you keep on increasing the voltage, 8 kV, 10 kV, 20 kV, PD will keep on increasing. Then if we start reducing the voltages again, 20 kV, 10 kV, it will not extinguish at 8 kV. So that is the extinction voltage. It may extinguish at, normally it extinguishes at a little bit lower voltages. So it will extinguish at, say for example, at 7 kV. So this will have extinction voltages. So from there also we can understand what is the nature of that different type of PD, that the PD inception voltage and extinction voltage. And that's why you need to do the studies of the impulses and AC, because at AC there is no PD. As soon as there is a transient, some minor durations or short duration transients occur, that time PD will start, transient will disappear, but PD will still continue because it has already started, and that inception voltage is reached by the transient, but the extinction voltage is below that normal operating voltages. So that's why there is a research on the PD with the impulse and AC or any other operating voltages. So some more part of the electrical will come whenever we will go to the particular equipment. So now related to the acoustic partial discharge. So this is some brief fundamentals of the electrical. Now we'll start the acoustic partial discharges, where it can be done on site because it is immune to electromagnetic interferences. Means it is a sound wave, pressure wave, So it will not have interferences with the electrical pulses. It will not have electromagnetic wave. So what is the fundamental of the acoustic pulsal discharge? PD creates many phenomena like sound, light, electromagnetic wave, voltage drop. So by utilizing all the changes created by the partial discharges, we have developed different eye of measurement. So one of these is that it creates the acoustic wave. It creates the pressure wave. This is normally at a different frequency zone, and it is normally told if the energy of the discharges is high, then the frequency will be low. If the energy of the discharges is low, then the frequency will be high. Pressure wave frequency, acoustic wave frequency will be high. That means speed is very low intensive one. So it is natural discharges is one of the natural discharges which we can visualize as lightning discharges, thunder. So that associated with the huge energy. So that's having a lower frequency acoustic pulses. That is means audible. Sonic zone. But here acoustic pressure wave is ultrasonic. It is having a very higher frequency. It is beyond the perception of our sonic zone. So because its energy is very low, so it will going to create a higher frequency pressure wave. So this pressure wave will move through the different medium and it will reach to the sensor. So in the different point, we put many piezoelectric sensor which will convert the pressure wave to electrical signals. So this piezoelectric sensor convert the pressure pulses in electric signals, and that electrical signals is used to measure that PD. So here basic advantage of this acoustic is that it will have the advantage of source locations. It because the pressure wave generated from that point, it will move to the sensor. It will take some time. So if you can understand that part, we can locate. If you measure that one, if many multi-sensor, if you put it, that will come the source location. How are you going to do it? It is non-invasive. You don't have to put because we can put the sensor outside the tank. If it is a transformer, it is a gas insulated substation, we can put the outside the tank. In any cases, we can put it. So that's why it can be done in online also. Even the system is in operations, we can do it. So this is a typical arrangement for the acoustic PD measurement. So say this is a transformer and this is a PD sources is created and high voltage source is given. This is the capacitor for the voltage measurement or capacity potential divider for the voltage measurement. If you want to do the electrical and acoustic together, then it will be coupling capacitor with the impedances. So like this, there is many combinations it can have, and there are many acoustic sensor which is mounted on the tank surface. Mounted on the tank surface, piezoelectric sensor. For a three-dimensional source locations, we need minimum 4 sensors. And if you have more number of sensors, then accuracy of the locations will increase. But minimum 4 sensors is necessary for the source locations. So source location part will come. So PD signals, acoustic PD signals will looks like this way, that will have a high frequency wave. And if you do the Fourier transform of this one, we're going to have around 50 kilohertz to 200 kilohertz zone. This is depending on the type of partial discharge or different partial, depending on the locations, depending on the field distributions of the sources. So you will have, this is one of the feature for the classification of the partial discharges using the Fourier transform. First Fourier transform algorithm, we can adapt it to find out the frequency. Now, to classify the partial discharges, we can have the many other features for the partial for the different cases. So discrete doublet transform is also all in use. So discrete doublet transform is a very common way to do the signal processing, digital signal processing of most of the non-stationary type of it. This is also a non-stationary intermittent type one. So here we can do the time frequency analysis of this one. So one signal we will going to have it will decompose into the approximate and total and high frequency, and the high frequency is still decompose into the half up. So this is the normal technique where all the fields will have the discrete doublet. So similar discrete doublet techniques we can adapted. Now, same way it has been adapted, but here the problem is, or challenge is that how to select the mother wavelet. So based on the energy label for the any signal, so this is a common for any type of signal processing, wherever the discrete wavelet or any wavelet transform is adapted. Selection of mother wavelet. So and selection of decomposition label. Decomposition label is been selected based on the energy of required cases. So how much energy label we should have, that is we can have a many decomposition label. This is the decomposition. If you are aware of the DWD, you know this is the decomposition. So this is the first decomposition, second, third, like this. You will have many decomposition label. It will continue. Level 1, level 2, level 3, like this. So many decomposition. How many are you going? It will not have it's 10, 15, 14, 7. How much you going to get it? So that is the cases. Now this is the mother wavelet. Means it is a filtering technique. You have original signal. It is a digital filtering technique. So mother wavelet is basically the what is the filter of these cases. So here also this is basically the filter. So it's a GN and HN. It is the low pass and high pass filter. So that filter is the what type of filter functions you're going to use it. That is the mother wavelet. So what type of going to? So that is the base few mother wavelet for the disc wavelet. So out of this, which will going to resemble with your non-stationary signals is been used. So there are different cases. So by the energy decomposition label, we can find out what should be the mother wavelet. Now, this is a few examples or few typical signals for the different type of partial discharges and the PD signals. So from their energy label, we can decompose it or we can find it out what are the different classifications of it. And classification is necessary to identify whether there is a severe zone or it is a not so severe zone. Or if it is severe zone, how much is the intensity of the severity? So that you want to do the classifications. Now, wavelet packet transform is also used. Now, many technique we adapt or we apply at the same times to have any misclassifications. Even one technique is giving you the proper results, but we adapt many techniques to simultaneously find out the classification so that there will not be less chances of error. If one is giving 90%, so still 10%, another will give another 90%, there will have a combinations of both will giving, then we'll have less chances of error. So that's why you're going to put wavelet packet is also similar decomposition labels you're going to get. Another additions here, this approximation is also been decomposed into two different labels. Previously, only the details were decomposition in wavelet packet, both the will. So you'll have many signals and different cases we can identify. It is also time frequency analysis. Now, some typical fact about the partial discharge acoustic pulses and their frequency, because based on the frequency you are classifying. So there are different signal SS will going to have the E measurement, acoustic partial discharge measurement. You will have a 20 to 2 megahertz. Normally sensors used, but in some cases 150 kilohertz narrowband sensor is also used. That is also being included. But research purpose, we can have a 2 megahertz plus response type. Now, different cases we can have that is ultrasonic range, because it is coming out to be in more than 20 kilohertz, 150 kilohertz, so it will be different ultrasonic range. So this peak will going to occur in this needle plane will going to occur at 40 kilohertz, and coronary discharge will have a different frequency you're going to see the peak. So based on that, measurement system is also designed, and based on that classification is also done. What is the frequency component? All the frequency. Now, partial discharge most critical cases is the transformer. Transformer also will have a many sound wave, like that it will have a magnetic noise, that is the humming noise, the vibrations of the tank, that will going to have very lower frequency compared to the partial discharge, 2.5 kilohertz. Then there will be a fan that is also giving a pressure wave, that is also vibrating. You will have 4 kilohertz. So that if you pump will have around 2 kilohertz. Any switching will occur around 2 kilohertz. That will also create a mechanical vibration, sound wave, but its range is very lower. compared to it. Whereas the OLTC, on-load tap changer operations, will give very close to the partial discharge frequency. So that also been classified based on the time domain. OLTC will have a longer durations operation. So along with the frequency as well as time, we can identify whether it is a PD or it is a mechanical operations of some other object, OLTC. So time difference is different. It is around 20 to 30 milliseconds for partial discharge will last that signals, acoustic signals, and whereas the OLTC will have a higher time. So source location algorithm or source location technique is very common for or very popular for the partial discharge detections in acoustic technique. So what is done in a very simple way, because this technique is a very details will not go here because it is total overall we are going to talk it. So it is iterative technique. It is very simple way of doing it. So I told you that it will be 4 sensor minimum is necessary. You can have more than 4 sensors also, but minimum 4 sensors is necessary. And each sensor's positions coordinate we have specified it, say xi, yi, zi. This is the 3-dimensional coordinate of the 4 sensors we can identify it. Now location is coordinate as x, y, z, which is unknown, which you have to determine it. Now capital T is the travel time from the nearest, which will have the first PD experience. So this will come after a few iterations only, after few more measurement, then we will come to this part. Capital T is the travel time from the PD to the first sensor, which will observe the signal first. That is the triggering time of it. And tau 12, tau 13, tau 14, this is the additional time. Or T plus tau 1 is the travel time from the sensor or PD source to the sensor 2, and similarly from the PD source to sensor 3 and sensor 4. So this is the distance square and this is the distance square by coordinate system. We can have this x1 like this, we can find it. So you can have the 4, you can see this is a 4 equations. Capital T is also unknown because we don't know from what will be the travel time from the unknown source to the sensor. But this we can measure it from the recorded waveform, the tau 12, tau 13, tau 14, we can measure it. So there is a 4 unknown, x, y, z, that is the coordinate of the sources, and t, travel time. Though we need only to find out the x, y, z. So by solving this one by any iterative method or any methods, we can find out the source. So this is the help for the source locations. For the similar, you can do the source location using the UHF technique also. UHF is ultra frequency. Though it is not immune to the electromagnetic interferences, because it will just having the principle of electromagnetic interferences, means it will just have, because the PD will create the electromagnetic wave also. So that electromagnetic wave will propagate to many directions. So that also it will going to put the sources. But here you cannot put it outside because this, if it is a transformer, total tank will act as a electromagnetic shield, Faraday cage type. So you know another of the intensified signal will come out. So that's why UHF signal is measured inside the transformer or through the non-metallic window. So that we're going to put it. So this is normally range of 300 megahertz. It is a higher ultra frequency. Propagation time is very low. So from source to sensor, it will take very less time. So that's why the phase resolved PD pattern also can be put it here also, because that time is almost negligible compared to the cycle time of 20 milliseconds. So for the PRPD analysis using the UHF signals, we can assume that almost it is reaching at the same time. When you go for the source location, even this 100 nanoseconds is used for the getting the time differences. So since UHF measurement is done on the transformer inside the transformer, but sometimes it may not be possible to put the sensor inside it. So that's why we have the dielectric window is placed there. Some cases UHF sensor is retrofitted through the drain valve, or we can put a dielectric window. So we put the internal sensor like this, so we can have the UHF technique. So again, here also similarly, different sensor will be put in different locations. So one is the source locations part, another is the initiation or the inceptions of the PD occurring or not. Because PD, if not available during the initial position, but it can occur at any time of the operation. So that's why it is for the higher cost equipment, specifically for the transformer, continuous monitoring of the PD and its analysis is necessary. So that online monitoring is very much required for the health and reliable operations of the transformer. So that's why you have to put it online. So inside the internal sensor, inside the transformer tank itself. So if there is a multiple PD, so that is another directions of the research of the identifying. So in a one transformer or one equipment, it is not possible to have only one PD source because it is a complex. You will have three phases. Yeah, many parcel discharge at the same time. So there is a technique to identify the multiple parcel discharge also in different sensor is placed on the tank surfaces. On the top of it, normally is placed it with the window. So the window is fitted on the tank. Put it. There is a many way of putting it, like it may be put in the drain valve. It may be put in the bushing zone. So this one of this you can put the window here, dielectric window and a quantum unit, that is a dielectric window, which is to be put during the manufacturing stage, which transformer will go for the UHF PD monitoring. So that will be placed during the manufacturing itself. So that is put it there. So many source locations algorithm, identification algorithm, multiple parcel discharges, it can be placed it different sensor. Basic idea of this is to identify the multiple PD is the independent component analysis. So there is a technique, it's very popular in a speech processing. Same technique is adapted here also for the multiple parcel discharges analysis. Now in a room, if many persons are talking at the same time, by the independent component analysis, we can identify which person's sound we like to listen. So in a noisy room also, by independent component analysis, we can identify it. So same technique is adapted here also to identify the multiple parcel discharges. So again, we will not go much details of this part. So, and this is something about the time difference, how it is measured. If the sensor 1 is showing, this is the wave, and sensor 2 is showing. So this is the triggering point of it, and it is coming after some time. So this may not be the true travel time. What is the capital T? So capital T, it is may not be true because it may started it. So this is after tearing of the measuring equipment, we are measuring it that way. So this is some travel time or some time after which that signal is coming. But anyway, that is not is required for us. How much it is that time? We need that distances, or what is the gap between these two? From this starting point to this gap, these distances in terms of time we need it. This times we need it. Signal arrived and sensor 1 is this time. Signal arrived and sensor 2 after the signal 1 is this. So this is the tau. That is the time differences between two different sensors for the same PD sources. Because of their different locations, different positions, it will need to different travel time. So there are many sensors available for the UHF PD measurement, which is very common. It's the mono state wire. We put one wire inside the. It is very cheaper. We can also build it of our own to measure the UHF partial discharge, but they have a different advantage and disadvantage. In lab, what we find it out, that is the sensitivity. If the partial discharge occurring at a very smaller magnitude and UHF sensor is placed a little bit away from it, say for example 1 meter, it is very difficult if there is no sensitive measurement. So all the sensors may not give the required sensitivity for here. So what you can have it that conical type. We adapt the conical type, which will going to have a more sensitivity for the lesser amount of partial discharge also. So they will have a different sensitivity, different bandwidth, depending on the difference. So it is a straight-wide, zigzag, helix, disc type, conical, and spiral. So we use the conical type sensor for measuring the UHF type partial discharges. So if we see this one, UHF type sensor, it is simply a metal in form of cone. But how much will be the diameter and how much will be the length of that cone? Means top is a smaller 1 point, but the outer side, which is this one, how much will be the diameter of it? So that decided based on the sensitivity. If you have a higher diameter, then you have more sensitivity. You have a lower diameter, less sensitivity. Now, how much will be the length? So that depends on what should be the frequency. What should be the length of the sensor? Since we are measuring in a higher frequency in the order of megahertz, so this length will tell you the what will be the peak frequency we are going to want to measure it. So that length of the sensor and the frequency is decided based on the wavelength and velocity. This velocity will be almost same as the light speed of light because electromagnetic wave frequency will be in the order of megahertz, and hence the wavelength you can find out. 1/4 of the wavelength will be the length of the sensor to design it. So we also do it in in-house to design or manufacture or made the sensor for our particular measurement. So this is a typical setup of UHF sensors, HB source, DSO, it is measuring it. And this is one of the setup. We have many setups of the different cases. PD sources, we put it, then high voltage is applied. We have many setup for this type of cases. Now, this is a typical PD signals. We can observe it. And if you do the Fourier transformations, we can have a different cases of the different frequency component of it. It's here it is around 10 to 40 megahertz is the peak frequency of the different cases. So this different graph will going to give you a different type of PD signals, and you're going to have the different frequency component to the analysis. Now we'll go for the partial discharges in rotating electrical machines. So this what we told previously, this all related to and can be adapted to most of the cases in transformer. Transformer we adapt most frequently that online measurement of the partial discharges. Now rotating machines also prone to the partial discharges and its effect on deteriorations. So before going to the rotating machines, we'll have a little bit understanding about the insulations in the rotating machines, rotating electrical machines. We're going to have a standard conductor or conductor of this one, and this will going to have insulations above this one. This one is with the conductor or strand. This will have insulation. So that is the two indicate the conductor insulations. This is a structure of high voltage rotating machines, either it is a synchronous machines or induction machines. Then we're going to have a coil insulations. That is also called, this conductor insulation is also called the turns insulations. Because this one and this next consecutive, this is the copper and this is another copper, this is the two different turns. So that is called the turn to turn insulations. Then from one turn to the core, the seventh portions is the core, metal steel, so that is the core. And 6 is the wedges or supportive one, which will not allow the coil to come out. So this 3 is the ground wall insulations. And this is made with a wrapping cases, like a tape. So this diagram I just to tell it because there is a one delaminations phenomena of the insulating material in rotating machines. which is going to give you the partial discharges. So that is the cases we can have manufacturing technique also. It is done with a taping. So this is the conductor is stacked together. Then the main insulations is made by wrapping it by different epoxy mica glass fiber based tape. They are using it. Then that is a different process to manufacture it. So that is necessary to understand the partial discharge. So this is the different insulation. There is a strand insul insulation. Each strand is then that is conduct. Then coil insulations. The conduct insulation and strand insulation is coming on to the turn insulation, then the ground on insulations or the coil insulation. And this is interlayered. So in a slot, there may have a two coil site in double layer winding. Normally it is what is happening in masons. So there will have an interlayer on insulation also. This 4-1 what is showing it. This may be of one phase, this may be of another phase. So there may have a voltage gradient between the two. So any zone can have a partial discharges. So this is a brief about the insulations in rotating electric machine. Now, what are the different discharges occur in a rotating electric machines? You can have internal discharges. So here significance is the same one as we have seen in the previous cases, that either it will have the void internally of this insulation. That is internal discharges that is done or occurring because of the manufacturing defect or during the operations because of the delaminations of the insulating material. Whatever are the reasons, inside the insulating material, internal discharge will occur. Then there will be slot discharges. This coil is placed in the slot. There will have a slot liner. So there have any chances that is a voltage gradient, then we call it as a slot discharges. The voltage gradient between the any zone, and if it is a lower, normally it is occur in the air. If this air is going to trap on that particular zone, breakdown will occur and that will erode the insulator slowly. So that is the slot discharges. Then discharge in the end winding in the overhang portion. So if you see in the different coil is placed, and if it is occurring in the end winding, which is also chances are having prone to the insulation damage. Most of the care is taken in a rotating electrical machines to make the slot insulations in the straight portions. But there is a little less care is taken in the overhang manufacturing. Now there is a technique called the vacuum pressure impregnation. So here there is all is taken care, but there is a previous cases press thermostating type cases. It's very less care is taken, but there is a chances of we can have a surface dragging. So you can have a discharge on the surface of the insulations. Then in a insulating material, because this will have a insulating material and this will have a ground core. So there will have a sudden change of the higher voltage to the zero. So if there is a sudden change, if that is from the higher voltage zero, that is a more voltage gradient, then there is a high chances of the breakdown. So that's why some stress grading in material is placed at the junction point, semiconducting type material. So that stress will not fall from very high to zero. It will have a little bit gradient type form. It will have a lesser slope. So there is a chances to have a breakdown or partial discharges in the grading junction also. In the overhang portion, so are the two different coil is placed there. There will be voltage differences. Similarly, because of the capacitive distributions, if there is a higher voltage appear more than the breakdown voltage of that particular localized zone, then there will be discharge. So that is a bar to bar discharges. So different discharges has been classified in the rotating machines. It can be slot partial discharges, So the measurement can be done online and offline, both. That internal discharges, internal faults, internal delaminations, which is because of the temperature differences, and demilation in the insulation itself and demilation between the conductor and insulations. So this internal discharge, this void is a natural lie of because of the manufacturing defect, so it will come initially, but this delaminations of the insulations because it is made of a tap, so that you can have a delamination that also created discharges. And discharge on the anode ending, this overing portions. When the stress grading coating, which is used for the reductions of the stresses at the junctions from the conductor and the core, and the gap type discharges, and the surface discharge, surface tracking. Rotating machines is allowed to have little bit higher amount of PD compared to the other devices. So this way it is a nano coulomb. Other cases, it is in the order of picocoulomb. In transformer or in other cable, we order allowable discharge is in the order of picocoulomb. But rotating machines can have little bit higher because of its nature. So if it is less than 2 nanocoulomb, then we call it is a good, excellent PD performance. It is free to PD, you can call it like the good, and this is the different range. So if it is higher than this one, and some cases PD is also measured specifically for the rotating machine in terms of volt, millivolt. So whatever there is a drop of this voltage, instead of doing it, the directly millivolt is measured. So PRPD patterns is also identified for the rotating electrical machines for the internal discharges and slot discharges, different cases. So by using the PRPD pattern, phases or PD pattern, we can identify what you're going to have the partial discharges in the different cases. Internal discharges, slot discharges, surface tracking, coronary discharges, field grading, or the different cases. So each type of discharge will going to give you different type of PRPD pattern. So from there we can identify the type of, you can adapt any AI technique to classify this one in online methods. So if it is surface tracking, which is more prone or less prone according to this say, we can identify it. So this is also few PRPD patterns. Either it can be a two-dimensional view on these cases or a three-dimensional view in these cases. Or the color bar indicates the intensity. How much is the intensity of these discharges? Higher intensified discharges, lower intensified discharges. Based on that, we give the color code for the different partial discharges. Now, some part of the cable. Now, cable is specifically used for the short AC transmissions or AC distribution and long or normal distribution. So in the case of DC distribution or DC transmissions, specifically for the penetrations of the renewable energy, we go for the HVDC cable. So how the cable performs on partial discharges, some extent we're going to understand from here. So cable will have a many very simple cases. You will have a many type of, but normal days we go for the XLP cable. So this XLP insulations here, unlike the other devices, which is confined to some zone, but cable will have a few kilometer long. So if you want to check it here, so here adapt technique is different. Transformer will be localized on that part. You can adapt it in one zone. Rotating machines will be localized in one particular zone, but cable will be traced to 1 kilometer. And out of that, any zone, if there is a fault, then you have to identify it. And this is most common type of failure in a cable. And if there is a cable failure, and if you find out the causes, in most of the cases is because of the partial discharges. So how it is been done? Here partial discharges can be used to identify the location also. There is a two different way of measuring it. Without giving any other measurement technique, we can identify the location of the partial discharges also. That is by the reflection. Okay, we'll take that part. Now PD pulse will create electromagnetic wave or electrical pulses that will going to propagate. It is high frequency. It is beyond. It is not the same as that of our power frequency. These pulses will have the higher frequency component that will propagate. And its magnitude is also very low. It will propagate to this part, and there a radio frequency current transformer or high frequency current transformer is put it here. So that will going to link it in the ground part. It is for the online measurement. So either it can be 2-3 different zones. So it can be, so this is one point is on it. In other zone also it can be connected in one side, and it will propagate in both the directions. Not necessarily it will propagate only one direction. It will propagate in both the directions. So locations, I will find it out. So now whenever there will have a partial discharges in one particular location, then this radio frequency current transformer or high frequency current transformer will record that signal. It will record that signal. So, and if you're having a two different zone, so they will record in the two different time. So by matching the time differences, we can identify where is the PD is going to occur it, or how is PD has started it. So that you can identify it for the cable. Cable also can be tested in laboratory for sample cases, not for a long. So here also there is a specified for a certain length, 1 meter, 1.5 meter, not for a in the total length. If some sample is been connected, specifically the HVDC cable, we apply the DC voltages for measuring the partial discharges in HVDC cable. So here also there will be a coupling capacitor. It will going to charge to the full voltages. It will going to have a breakdown. Now here PD will going to occur not because of the variations of the cycle, variation of the AC voltage. Here DC cases, PD will be different because here one breakdown will going to occur based on the applied voltage of the DC, applied operating voltages. Then this voltage on the zone high partial discharge is occur, that will going to disappear. It will be zero. Then PD will disappear, and again voltage will going to charge. So same way you will have the coupling capacity will recharge it, and that will create a loop. So it will going to give a current pulses which is measured in a oscilloscope or PD detector. Now since it's a DC voltages, we cannot put a blocking part here, because if you put a inductor, then omega is 0, it will be almost sorted. So it is sorted unless there is some ripple. We cannot put a capacitor for this blocking cases in previous cases, because it will not allow any power to flow there. It will block it because that omega is 0, it will be infinity. So L will also going to create short circuit, it will not block anything, and capacitor will also block totally. So that's why high value resistance is connected for protection purpose or filtering purpose. So neither of this will go to this side, nor it will come. So high value resistance is connected here for protection purpose as well as for the filtering purpose. Means none of this, if this is signal is not coupled here, it's called coupling capacitor. And when there is a drop, this will going to give a couple. It will going to make a minor loop here. The current will flow only the smaller loop. That's why it is called the coupling capacitor, coupled between these two. So if it is going to other side, then we will not able to identify how much is the current, because this side, if you're going to pass it, then you will. So that's why we put a higher impedance one. Its impedance will be compared to this impedance at high frequency will be higher. Now here we cannot do the, okay, the PD IV and PD EV and breakdown voltage also we can measure it. And here we cannot do the PR PD because there is no phase in case of DC. We cannot match with the phases because it is a constant DC voltages. So in case of cable, there is a either it can have a scratches inside it, bubbles, and protrusion. Protrusion means if there is some foreign particles put inside of it, or the conductor is having some sharp edges. Conductor is not smooth enough, so it is going to give a different enhanced stresses. So that will also going to create a partial discharge. So for a typical cable, the partial discharge inception voltage, partial discharge extension voltage, you can see extension voltage is normally lower than the inception voltage. Either in DC cases, AC/DC cases, or AC cases. Inception voltage is lower than. Reason is, if you are in this high voltage and this field, you know it that because of the already present charges, discharge will continue, but discharge will initiate. This is a very common phenomena which we know it for the those who are in high voltage. The Towson's breakdown mechanism, that initiations is done by the some charges, some electron. So that takes some time to break. That is called that's why inception voltage is a little bit higher than the extension voltage. And the extension already is discharge is continuing. So for that, you don't need to have any support from outside. Already electron beam is available. So that's why it is a little bit lower. So breakdown voltage and partial discharge. So partial discharge will occur much lower voltages compared to the breakdown voltages of that particular insulating material. So it is a comparisons of the different void cases. If the void is significantly smaller, then BDV and PDIV will be higher. If it is void is significantly higher, then we are going to have a lower BDV, and PDIV is also lower. So in the temperature wise, it is going to vary. If it's a higher temperature, operating temperature in case of a cable is around 60 degree, 80 to 60 degrees Celsius, so that you can have a change in the PD insertion voltage. So the insulating engineer and insulating material design engineer will take care about this temperature profile while designing the insulation. Now, since PRPD is not valid in case of HVDC or DC apply, so there is a parallel to it that is called the pulse sequence analysis, PSA. You don't have the phases, constant voltages, but here another technique is adapted or for the classification. Here the same reasons for the classifications of the partial discharges, whether it is occurring in the surface, void, or corona, or any other type of discharges, and to understand the severity of it. So that's why phase pulse sequence analysis is done for the HPDC or DC cable or DC PD measurement. So what is this pulse sequence analysis? So two consecutive pulses. All the pulses is been recorded because there are no phases, all the pulses are recorded. Now, what is the time difference between two consecutive pulses? That is delta T pre, we take it. So this is the nth or this instant we are analyzing it. What does the previous pulse measure magnitude, and what is the difference delta P pre and previous and successive? So that two pulse in all cases we're going to check it. What is the cases? And now this is next what will happen to the, and what is the time differences? This time won't be same in all the cases because it is, and all the magnitude also won't be same. Qn minus 1, Qn plus 1 won't be same. Qn plus 2 won't be same. Similarly, this all the time gap won't be same. Now, based on these cases, we do the analysis of the pulse sequence analysis. We do the pulse sequence analysis. So we can have the magnitude. So this graph or this is itself is implied it that we just record the pulses and we record this one, that what is the differences between the previous, that is delta pre, what is the difference or the successive, that is the delta successive. So magnitude and the time differences, we're going to put it. What is the time differences and the magnitude, we're going to plot it. So that is the four plot we're going to do it. Then discharge differences and time differences. Either the pre or the discharge differences, this discharge time, we're going to plot it. What is the Q and the time differences? We're going to plot it. Now delta Q, its meaning is that we can have what is the pre and successive. Previous differences and successive differences, that you can also have a plot. Previous differences and successive differences. We can have a plot of the previous time and the successive time. That also you can have. This is all the four plot is used for the pulse sequence analysis for the HDC cable. So this is a typical PSA diagram for a cable, HVDC cable. And there is a void, and depending on the applied voltages and the size of the parts. So if you applied voltages, so this is the delta Q and delta Q, pre and successive. By this you can be plotted, we will get one cases. And this is the time difference, delta free and delta free. Similarly, you can have a plot of the other cases also. So this is going to give you the different pattern. And hence, by adapting the pattern recognition technique, we can classify the partial discharges occurring in the HVDC cable. And we can also assess the severity of the partial discharges. So in summary, if you're going to check it, what we have understood it, that is, we understood from the PD fundamentals, from the basics of from the definition of the partial discharges, its effect on insulations, and why you go for the PD measurement. And what are the different techniques? We talked about the electrical PD measurement, then acoustic and UHF PD measurement. Different signal processing technique is used to find out the feature and classifications of the partial discharges like FFT, DWT, WPT. Acoustic and UHF is used for the source locations algorithm. PD has been classified in case of AC by PRPD analysis, phase resolved partial discharge analysis. And pulse sequence analysis is done for the DC PD measurement. Basically, it is nowadays used for the HVDC cable because cable is very popular for the DC transmission. And this is basically for the renewable energies penetrations, because from the overseas and other locations, cable is the most popular, but there you cannot use for the AC transmission because of the charging current, and hence the DC, and hence the DC cable, and hence the DC PD edge analysis, and so PSA is coming in. PD in transformer, because for the source locations, UHF, whatever technique we adapted it, oil press board insulation systems for the transformer, then we did for the partial discharge in rotating electric machines, the different insulations and the classifications, and partial discharges in the cable, specifically for the HVDC cable. In case of AC, similarly, we can adapt it, and DC also we can do it for the PD measurement. So this few technique, and this can be adapted, this partial discharge can be adapted for the GIS, gas insulated systems, or gas insulated substations. It can be adapted for the insulating material of any other devices, the capacitor, insulator. If there is some void chances or there is a manufacturing defect, we can identify it. So this is for, if you have any question, you can ask.
Yes, participants, if you have any question, please ask.
Thank you, sir.
Thank you.
Sir, please, participant, if you have any question, you can directly interact with our expert speaker. They can raise their hand and we can
Yeah,
unmute
please
them.
raise your hand. There is a question in the chat box.
Hmm. Is
Uh,
PD
uh,
is PD possible in distribution transformer for continuously non-linear load?
Say PD has nothing to do with the load or any other cases. PD is only depends on the voltages. If the insulation is not designed properly, PD will going to occur. It only depends on the voltage levels. Whatever be the cases, it will have the more than the inception voltage, PD will occur. Now the cases is whether we should measure the PD or distribution transformer or power transformer. Now it comes a cost effectiveness. Definitely there will be partial discharge in distribution transformer or any lower cost equipment also. Then if we cannot adapt or cannot monitor the PD for a low cost, because if the monitoring system is for 10 lakhs rupees and our device is for 5 lakh rupees, then it is meaningless. If the monitoring system is 10 lakh rupees or device is 3 crores, then it is a meaningful. Like that, it has been also techno-economic, we're going to adapt it. But whenever there is a voltage, there will be PD. And now it has been observed even the low voltage also. PD will going to occur. If there is localized electric stress, even now it has been shipped, that is PD is not a voltage phenomena. It is a field phenomenon. It is a stress phenomenon.
Mm.
In a low voltage system also, if the stress exceeds more than the breakdown voltages, because V by D, V is very low, but D is very small, then V by D will be very high in average sense. Then there are also PD. In the rotating machines, low voltage rotating machines of 415 volt also will experience the partial discharges.
Yes, any other question?
How PD is wisely used in smart cities while laying HV cable and how it can monitored?
So those are the manufacturer of HP cable. They have a continuous quality assessment technique, means the PD is already standardized measurement. So while commissioning any cable, they will go under testing as per that standard, specific standard. And if the PD is specified on the standard, they will do it. Now for the online monitoring, we have installed the high frequency current transformer to do the online monitoring it.
Okay.
Thank you, sir. Okay, I believe there is no more question. Harmonics, yeah. Harmonics can damage insulation, so of might be chances of PD generation.
Say harmonic or transient. If there is overheating because of the harmonics, because partial discharge having effect on temperature, I've shown there is many analysis on this part. We also did few analysis related to the temperature. PD effect with the temperature means for the lower temperature, what will be the chances of PDIV? At higher temperature, we will have a lesser voltages at PDIV. So if the harmonics create a temperature effect, higher temperature, then PD definitely will reduce on that particular part. And if there is a voltage pickup, means harmonic by the peak of this waveform, then there will have a voltage increase. Then there also will have a chances of partial discharges. So in any cases, either it is by the temperature or by the increase of the voltages, then there will have a partial discharges. There is a IEC code for PD measurement. IEC code as well as the IEEE code for PD measurement. And there is a IS standard for PD measurement also. Yes, for different devices, there is a PD measurement. Now it is a standardized technique for it. So IC code is available. And if it is not a general, there is a general technique for high voltage testing technique. And there is a equipment specific also. For example, switchgear, how are you going to do it? For cable, how are you going to do it? Transformer, there is not a general. There will have a specific also.
Okay. Okay. So if there is no more question, okay. So thank you very much, Dr. Kundu, for this very informative session.
Okay, thank you, Chirag. Thank you,
Thank you,
Mr.
sir.
Chirag.
Thank you, sir.